Hello, I'm Nidhi Rajshree. I manage the natural language understanding team at Roku's Voice. Today, I'm going to talk about spoken language understanding challenges in entertainment domain. As voice-enabled systems are gaining more and more popularity, the success of these systems relies not only on the correct recognition of what user said, but also of what user meant. Spoken language understanding focuses on interpreting these users' intentions from their speech utterances and SLU, or spoken language understanding, as compared to traditional text natural language understanding system, has its own challenges since spoken language is noisier than written language. Moreover, when SLU is applied to the task of understanding command style, short utterances having low context, it adds to the complexity. And then there is the complexity that gets added as the challenges of the entertainment domain come in. So let me go to the agenda slide. Here in this agenda here is the agenda for the session. I'll first describe some of the key objectives of spoken language understanding, followed by a high-level overview of an oversimplified SLU system to set up the context. And then I'm going to talk about the challenges faced in achieving those objectives. I'll also talk about some of the state-of-the-art techniques used in addressing these challenges. The primary objective of a SLU system is, of course, to understand what the user said. And then the next step is to be able to understand what the user said in different languages. And then a more advanced objective is to understand beyond what the user said. So understand what was not said, but what was meant, or deeper language understanding. Now, meeting each of these objectives has its own set of challenges. Here are a few examples. For example, with Melissa Fent as an utterance that we get, it's really an ASR, or automated speech recognition system error, where the user is asking for the content Maleficent. And then the challenges that you see with the cross-language understanding, or understanding what was said in different languages. Here's an example where the user is asking for playing the Spanish version of Die Hard movie. And as you see in the utterance, there is a code switching or language switching that's happening. There's English and then there's Spanish. So that's another kind of challenge with cross-language understanding. And then with deep language understanding, in this case, most probably the user is asking for the movie Rocketman, which was based on Elton John, but ends up saying, play the Elton John movie. So next, we're going to look at a high-level overview of the system in order to set up some context. And then I'm going to use this system diagram to walk through the different challenges which are faced in meeting those three objectives. And this is an extremely simplified version of a SLU system. As a first step, what you see here is that the user issues a voice command, play pump up the volume on Hulu. And then there is an automated speech recognition system that takes the speech and converts it into text or transcription. In this case, the ASR does a good job and it gets it right. Now, this transcription goes to a natural language understanding system, which basically predicts or labels the transcription to basically identify the intent, user intent, and the entities. So in this case, for example, this is the NBEST list of predictions from the NLU system, where on the top, what you see is pump up the volume being tagged as a video request, and that's a movie. Hulu is a channel. And then the second prediction is predicting it as a music request. And the third prediction is a system command, where the user might just be wanting to increase the volume. Now, all of this goes into a third component, which is also known as the action or fulfillment component. The goal of this component is to fulfill the user's command. And in this case, since it's just going to do a search for the user, that's why I have the search component there. But then this could have been something else. It could have been more complicated, where it does natural language generation of a response, and then also uses a TTS, a text-to-speech engine, in order to give the response back to the user in a natural language. So it could be as complex as that, and then it could be as simple as this, and it could also include something like a dialogue manager. Now, for the purpose of this presentation, I'm going to keep it very simple, and that's why I'm calling it a search component, which just searches for the content, in this case, pump up the volume movie, and then shows that back to the user. So now that we have this high level, oversimplified view of a slew system or a spoken language system, let's get into understanding the challenges. And I'm going to start with the challenges within the entertainment domain first. So the first challenge that you see here is, how these different entities look in different subdomains within the entertainment domain. So, for example, music has these really creative and funky names like Clock9 and Snot that are spelled differently, they look different. And then there are channels which have acronyms or they're really short, for example, CBS and Fox. And then you have these system commands which are more contextual in nature, like set a timer for 3 p.m., raise the volume on my television, and so on and so forth. And then you obviously have things like genres, which are more open class, and then you have movies. So each of these entities or each of these subdomains look very different, and that's why there wouldn't be a one-size-fits-all problem to address this, to address all the entities or understand natural language in these different subdomains. And then there is the issue of ambiguity, where there's a lot of overlap between music and movies. For example, Bohemian Rhapsody is a movie and also a music, and similarly, sci-fi is a channel as well as it could also be a genre. We saw the case of Pump Up the Volume in the last slide. And then these ambiguities don't only happen across subdomains, but they are also within the same domain. For example, in this case, Death on the Nile was a movie that was released in 1978, and then there was another one in 2020, I think. So that's the second kind of problem that we face with the domain. And then the third kind of problem is spoken versus written form. So what you really see here is that there's this example of baby no money, which is really spelled as baby no dollar, or just the word plays that happens in the entertainment domain with Mayor of Easttown, where Mayor is just spelled differently. So we see a lot of those. And then there's dynamicity in the domain. For example, Taylor Swift, you would assume that the prediction should be a music request, except for in 2020 when there was a documentary based on her Miss Americana that came in, where users were really expecting a video request. And again, with COVID-19 pandemic as a movie became really famous, and so on and so forth. So haven't seen that these challenges in the entertainment domain. The next step that I want to talk about, or next set of slides that I'm going to talk about, is going to be more technical challenges in achieving those three objectives. So if you guys remember, the first objective here was to understand what the user said, and this is where and this is one of the key objectives. And that is why ASR, or Automated Speech Recognition System, has a really crucial role to play in this. Now, even though ASR systems have significantly improved over the last decade, they still introduce a lot of errors when they transcribe speech to text. Now, here's an example where the user is requesting for the movie Nosferatu, which goes through an ASR system, and then you can see the transcription is all over the place. Now, when an error occurs at this stage, it's extremely hard to recover it downstream. And no matter if the natural language understanding system picks up other contextual cues here, play probably is associated with video more, and so on and so forth, and still identifies the correct entity spans and things like that, it won't be able to fulfill it because there's really no movie called NAS for OC2. So let's understand why this really happens. At the base of this is the fact that there are similar sounding words and phrases with different meanings. Now, for example, homophones, which are similar sounding words with different meanings, you have these different versions. And here's an example: Greece versus Greece. And as I'm speaking it, I'm pretty sure you won't be able to make out the difference. Even a human ear can't make out a difference. It's really difficult for an ASR to do that. But those are the kind of challenges that homophones present. And then oronyms, which are basically similar sounding phrases with different meanings. In this case, one example is Gemini man versus Jim and I man. So those are other kind of challenges that exist. And then these homophones and oronyms, the effect of this gets aggravated with fast speech in spoken language understanding. For example, we often see that and becomes on, so Hobbs and Shaw becomes Hobson Shaw. And then, of course, the fact that entertainment domain has a lot of creative names, and there's a lot of wordplays. So you have, Mare versus Mayor and Mayor of Easttown and Maid of Honor, spelled differently. And there's an endless list to this. So next, let's try to understand some of the general techniques that I use, some of the state-of-the-art techniques that I used, and all of these algorithms you'll find a reference towards the end of the slides, if you'd like to get deeper into them. But one of the first techniques that I'm going to talk about is machine translation, where the goal is to treat the translation of an erroneous transcription or conversion of an erroneous transcription to a corrected transcription as a problem of translating from one language to another language. The same techniques of sec-to-sec model can be used for this. And in this case, which is basically going to be trained on these pairs of erroneous transcriptions and corrected transcriptions. For example, in this case, Cross-Smith movies and Christmas movies. And then these could basically help do some ASR correction. Now, there are other machine learning techniques beyond that. For example, the phoneme embeddings techniques, where the idea is to build this phoneme embeddings, where similar sounding phonemes, they're really clustered together, and hence you could basically run something like a k-nearest neighbor or some sort of vector similarity algorithm in order to find how close the candidates are to each other, to the transcription. And again, this can be built using sec model. In fact, the reference here talks about different ways of doing this. Now, apart from machine learning techniques, there are, of course, other techniques like the phonetic fuzzy matching technique, where these are much simpler techniques, but then they rely on these powerful phonetic encoding algorithms like double metaphone, or soundex, which basically can transform that text into a phonetic encoding. And as you see here, Catherine spelled with a C and Catherine spelled with a K. Both of them, even though their orthography or their written forms, the spellings are different, but their phonetic encodings that come out after applying these algorithms is exactly the same. The same case with Jonathan, John, and Jonathan, without an H, and so on and so forth. So these are simple algorithms, but they help if there are two utterances, or if there's an utterance in ASR erroneous utterance or transcription, and an entity that have almost a similar kind of phonetic encoding, then we know that they are close to each other. So now what I'm going to do is that I'm going to show you some examples of the kind of erroneous transcriptions that we see and the kind of fixes that happen. And we already saw Nosferatu and Melissa Fenn for Maleficent, and then there's this other list: Aristicuts, Coniger, Aeronauts, which all come out in different ways. Okay, so next I'm going to talk about the challenges in cross-language understanding, or understanding what the user said in different languages. And there's, of course, the more prevalent issue of bootstrapping a model for a new language, because there isn't always enough data in the target language to train the models. But code switching or language switching is also a reality in the entertainment domain. When the user wants to watch a foreign movie, say a German user wants to watch an English movie, or a user in United States wants to watch a Spanish movie. And one of the examples here, as I was showing earlier in the slide, show me the Spanish version of Die Hard. When the user is asking for that, even if the ASR gets it right, the natural language understanding system, if it was trained completely on a Spanish data set, it may not be able to get the right prediction. So in this case, for example, it thinks that the show is basically a content type, like a TV show or a documentary or a video. And then it gets the wrong spans for the entity of the movie, and the movie entity. And of course, because there's no movie by that name, it's going to bonk at search. So to address both these challenges, of bootstrapping the model when you don't have enough data, and code switching or language switching, the state-of-the-art transformer-based models comes to our rescue. And more recently, there have been several multilingual transformer models that have been built, such as multilingual BERT or MBERT, cross-language model XLM Roberta or XLMR models. And these pre-trained contextual embeddings from these models can be leveraged to do transfer learning. Now, what you see on the left-hand side in the traditional ML approach is that you have a lot of English data and you end up training an English learning system. Pretty good. And in that ideal world, you'll probably have a lot of Spanish data and you'll be able to train a Spanish learning system. But in reality, what happens is that you have very little Spanish data. And this is where, giving a few training data in Spanish and then sort of being able to transfer learn from English, or the knowledge that is built, that is basically encoded in those cross-lingual word embeddings from these transformer-based models, that can be transferred towards Spanish prediction. And as you see, the cross-lingual word embeddings, they preserve the concept across other languages. And as a result, they also help in addressing the problem of code switching or language switching. Okay, so now let's look at the final challenge, which is basically, challenges in deeper natural language and deeper language understanding, where we want to go beyond shallow understanding to understand what the user meant, even if they didn't really say that. They didn't exactly or precisely put forward their query, or maybe something like a loose speak. Now, it is not common for users to issue these imprecise query in the entertainment domain. Many a times the user do not remember in that very moment the exact name of the movie and ends up using other cues to get to the content. For example, as we saw in the Elton John movie when the user wanted to probably see the Rocket Man. Or sometimes they just want to, find content around certain topics of interest, like courtroom dramas or movies based on shark and so on and so forth. Now, in this example, what we're seeing is the user ends up saying shark movie, and if the NLU system just does shallow understanding, then it's most probably going to bring up something called a shark movie, which is a movie in its prediction, but there really isn't any shark movie. And most probably the user is really looking for movies like Jaws and other famous shark movies. So in this case, the NLU really needs to interpret this as movies about a certain topic, and in this case, about shark. Even though the natural language is there's not much difference in how users would say that. So in order to address this problem, one of the established techniques used in this is leveraging semantic technologies such as knowledge graph. Where the semantic technology or the semantic knowledge is really stored as a graph of nodes and edges, there's several ways to reason on such knowledge graphs, some using graph traversal algorithms, etc. For example, in this case, what we're seeing is that to the entity shark, there are several paths, and these paths are from movies that are directly based on these on shark the animal, or movies that are based on books that are written on shark, or movies that are based on a true story event that was based on shark. Now, such signals could be leveraged in an NLU system or NLU model in order to be able to do that deeper interpretation that users really not asking for that specific movie, but is interested in it as a topic. And that's when that can work with query expansion and other techniques in order to get more relevant content like Jaws, the deep, open waters, shallows, and so on and so forth. These are some of the examples of the transcription. For example, shark movies that we just discussed, and then the Elton John movie that we were discussing, the Harley Quinn song, that the user's probably asking for bird of prey songs. So to summarize, while there are several interesting problems with respect to spoken language understanding, I wanted to highlight those that are at the cusp of the entertainment domain and SLU as a technology, and also wanted to talk about some of the well-proven techniques to handle these. As I mentioned earlier, that if you wanted to do a deep dive into these different algorithms, read more about them, here's a list of references that are available to go through. With that, I'll end the presentation, and thank you very much for listening.